In this video, I'm going to talk about conductors, semiconductors, and insulators. Conductors are nothing but these materials, they allow electrons to move from one element to another element freely. The best example is, you can say, aluminum and copper, iron. All the metals are very good conductors. Atomic number for aluminum is 13. Okay, that means if you look at aluminum atom, it has 13 electrons and 13 protons. Neutrons are also almost same. Now if you look at the electrons are revolving around the nucleus. The first orbit can handle 2 electrons or can hold 2 electrons, so 2 electrons are going to stay there, and 8 electrons are going to be in the second orbit. Remaining 3 electrons are going to be in the outermost orbit. Now this aluminum atom wants to get stability. It will be stabilized when there are 8 electrons in its outermost orbit, or if the outermost orbit is completely full. Here, so this third orbit can handle up to 18 electrons. If you remember, 2 to the power of n square, where n is the orbit number. So if you look at the third orbit, n equal to 3 square is 9 times 2 18. So this can handle or hold up to 18 electrons. Now getting 15 more electrons is too difficult, but it's easy for the aluminum to lose these 3 electrons. So try to get rid of those 3 electrons and to get the stability. So basically what happens here, if we look at this outermost orbit in a microscopic view, okay, so here in this orbit there are 2 bands. One is called conduction band, another one is called valency band. So if you look this in a microscopic way very close, so there are 2 bands. One is conduction band and valency band. Now in conductors, this conduction band and valency band are together. There is no energy gap. So if an electron is in the outermost orbit in the conductor, that means it is already in the conduction band, already in the valency band. So you can think of, so if you look at this, if I magnify it, okay, so here is the conduction band or maybe valency band. So here is the valency band. So all the electrons are going to be here. But for the conductors, this valency band and conduction band are touching each other. So electrons can move from valency band to conduction band without having any external energy. So they can easily move from here to here and here to here, and from valency band to conduction band to valency band. So that's what the conductors are. The conductors have a conductivity of sigma is greater than 10 to the power of 3 Simon per meter. Conductors have a high conductivity, which is 10 to the power of 3 Simon per meter. Rho value, that's a conduction for the conductors. So next one, I'm going to talk about insulators. Okay, insulators are very bad conductors. So here, if you look at this outermost orbit, as you mentioned, we have valency band and conduction band. This valency band and conduction band, there is a big energy gap between the valency band and conduction band. So if you look at this outermost orbit, so the electrons are probably inner side of this orbit. This electron is really in magnetically or connected with the nuclei. Okay, it could be a different material like arsenic. Okay, so arsenic has 18 electrons, so atomic number is 18. So here you end up with 2 electrons there, 8 electrons there, and 8 electrons here. Okay, so as long as there are 8 electrons in the outermost orbit, it's going to be stabilized. Okay, so here the 8 electrons in the outermost orbit, we will see inner side of this orbit. So to get these electrons from inside to the outer side, that is called from the valency band to the conduction band. So assume that this is the valency band and conduction band is on the other side of the orbit. There is a energy gap. Here he mentioned band gap, but it's basically energy gap. Okay, so this energy gap is really high in the insulators. The energy gap here is almost 7 electron volt. Okay, electron volt is the smallest unit for the energy. Basically 1 electron volt equal to 1.602 times 10 to the power of minus 19 joules. Okay, so you can see 1 electron volt is a very small number. Okay, so it needs lots of energy to break this bond. That means to move this electron from valency band to the conduction band, it needs lots of energy in the insulators. Okay, so the conductivity in insulators, this is for conductors. Conductivity for insulators is 10 to the power of minus 8 Simon per meter. Okay, so conductivity is greater than 10 to the power of minus 8 Simon per meter. When it comes to the semiconductors, by the way, I got this picture from this web page. Now, when it comes to the semiconductors are nothing but they have 4 electrons in its outermost orbit. The best example for semiconductors are silicon and germanium. If you look at silicon, silicon has atomic number 14. So if you look at silicon, so 2 electrons in the first orbit, 8 in the second orbit, and then remaining 4 in the third orbit. These 4 electrons needs another 4 to be stabilized, or it needs to get rid of it or gain another 4. So sometimes it's easy to get rid of, sometimes it's easy to gain based on what type of doping we are doing. Okay, so when it comes to the energy gap between the conduction band and valency band in the silicon atom is very small, which is 0.7 electron volt. Another semiconducting material is germanium. That value is 1.13 electron volt approximately. Okay, it needs this much energy to break the band and move from valency band to conduction band. How do they get that energy? That energy, it can get it from the sunlight or by applying pressure, all those things. Okay, not every element which has 4 electrons in its outermost orbit is not a good semiconductor. If you look at carbon is a conductor. It's not very excellent conductor or very good conductor, but carbon is a conductor, but still it has only 4 electrons in its outermost orbit. So if you look at this fourth group and 14th column, okay, there you will find this elements which has 4 electrons in its outermost orbit. But silicon and germanium are the best semiconducting material, and silicon is the very cheapest material. Silicon is nothing but the sand. I found this periodic table from this web page, and these are all these highlighted materials. Not everything is semiconducting material. This is a pure semiconducting material, but when you make them into Li, so when you combine 2 materials together will form Li. Okay, so I mean combination of these alloys will make a good semiconducting material. As I mentioned, silicon is the cheapest one, and most of our electronic components, okay, your cell phone materials in your cell phone, materials in the motherboard of a computer, most of them are made with silicon. Okay, I'll stop this video. Oh, before stopping here in semiconductors, the conductivity range is 10 to the power of minus 8 between 10 to the power of minus 8 Simon to 10 to the power of 3 Simon per meter. Okay, this is the conductivity range in the semiconductor. So if it is conductivity is more than 10 to the power of 3 Simon per meter, that's a good conductor. If it is below 10 to the power of minus 8, a good insulator. If it is in between, that's a semiconductor. Thank you. I'll stop this video here. Next video, I'll talk about Coulomb's law in the next video. Thank you.